So, good morning, everyone. Good afternoon, who is in Europe. My name is Bruno Vicenzi. I'm a technical manager of the European Powder Metallurgy Association. I'm the manager of the dissemination work package of this European project, START, that will begin today a series of webinars to disseminate, first of all, what we're doing, and secondly, more efficiently in the future about our results. Actually, we're planning two other seminars, webinars. One should be the 26th of April, if you want to save the date, and we will talk about South America in particular, and the next one will be the 1st of June, probably, and we will talk about Europe. Today we have two presenters, both from Portugal, from the Laboratory of Energy and LNEG. The first one is actually the coordinator of the project, Filipe Neves. He will give you an overview of the START project. And the second one is Daniel Oliveira, and he will give you a presentation about the challenge of collecting uniform samples for use in the START project, which is basically the topic of today. Thank you everyone again for being here. There will be a discussion at the end, so if you have questions, you can type them in the chat if you want, or you should be able anyway to open your microphones later when we will change the mode to the discussion mode. So without losing more time in presentations, I will now give the floor to Filipe Neves from LNEG, who is coordinating the project, and I will move us back again to to the previous situation. You see the slides now, right?
Yeah.
Okay. Thank you, Filipe. Your floor is yours.
Bruno. Okay, thank you, Bruno, for the introduction. Good morning, good afternoon to all of you that are present here. My name, as Bruno said, is Filipe Neves. I am the project coordinator of the START project, which is entitled Sustainable Energy Harvesting System Based on Innovative Mine Waste Recycling. I am a researcher at the LNEG, the National Laboratory of Energy and Geology. So here is the presentation outline. I will start by giving you what was the purpose for creating this project, the main motivation. I will give you a general overview of the START project, the consortium duration, main objectives, the START concept, and then I will move on to speak about a little bit about green energy harvesting. What is the definition of thermoelectric energy harvesting? What is waste heat and the waste heat recovery potential? What are the main characteristics of the thermoelectrical device? The figure of merit, and also the main potentialities of using tetrarite-based materials for this type of application. Then I will give you the main impacts and outcomes of the START project, and also I will explain how you can follow us through our webpage, our social media accounts, the newsletter, and then I will conclude with the acknowledgements. So what was the motivation for preparing this project? So as you know, climate change is one of the greatest challenge faced by humankind, and to fight the global warming, it's critically dependent on the rapid implementation of a green transition, to which the European Union is fully committed through the European Green Deal. However, this green transition is based on a shift from a fossil fuel intensive to a material intensive energy system, which implies an increase increased need of mineral resources. So, and this growing demand for essential minerals and the declining quality of the ores is leading to a substantial increase in waste volumes from mining operation. So, if we have the chance of using those mine waste materials and turning them into valuable secondary raw materials, as we are proposing in this project for the development of advanced energy conversion devices, this will create an increased economic incentive to eliminate the environmental hazard tailings. Another issue is related with the current commercial thermoelectrical devices. For those who don't know, they rely on tellurium-based thermal elements. You will see later on my presentation. And this element, tellurium, is derived or refined from minerals that are scarce in Europe, making the continent heavily import independent. So it is critical to find alternative materials for this type of tellurium-based materials to be applied in thermoelectrical devices in order to increase the sustainability of these devices and its application. So now moving to giving you some details about the START project. So this is an innovation project that was approved on the Horizon Europe program, Pillar 2, and the topic was about building innovative value chain from raw materials to sustainable products. And the main challenge of this call was to develop innovative and sustainable technology and business solutions for new high value added and sustainable products with unchanged functional properties based on the European Union produced raw materials, with a focus, for example, on raw materials necessary for the renewable energy ecosystems. So, and that's what we are dealing here on the START project. We intend to convert waste mine materials into sustainable products for developing renewable energy ecosystems through thermoelectrics. Here are some details about the consortium. Considering that we cover a different range and different areas, different topics during the implementation of the project that goes from geology, material science, and economics, innovation, life cycle assessment, we needed to build a multidisciplinary consortium. In this case, the START project is constituted by 15 partners from 10 European member states and 1 associated countries, as you can see here on the Europe map, including 6 research organizations with strong background and knowledge on geology, material science, and renewable energies, 6 CMEs, companies that guarantee the entire supply chain from production, exploitation, and ecological footprint assessment, and 2 non-profit international associations with a consolidated network of partners and stakeholders. So the project will have a duration of 48 months. It started in June 2022, and you find here the budget, the total budget for the project and the maximum grant amount. Now, the main objective of the project, of the START project, is to build an innovative ecosystem in the European Union related to the development of sustainable and economically viable tellurium-free thermoelectric waste heat harvesting system. How are we going to achieve this? By producing advanced sulfide P-type thermal elements that incorporates discarded waste secondary sulfides, mainly those belonging to the tetrarite ternatite mineral series, to replace the current commercial tellurium-based P-type thermoments. In order to do this and to implement all the activities on the START project, we build a concept, the START concept, that is mainly based on transforming mining waste into waste heat recovery materials. You can see here on this diagram the different activities that will be implemented in the START project. That starts, of course, by finding suitable mine waste sites and to recover and reuse of the mine waste material that will be incorporated then in the material processing cycle of the P-type thermoments based on the tetrarite tenantite mineral series. This will involve different technologies that goes through two main technologies that which are powder technology and rapid solidification. The p-types thermal elements will then be incorporated on the thermoelectrical device. The the production of the thermoelectrical device will involve device design, simulations, activities, and also the characterization of the performance of the device. Then there is the scale up of the different technologies involved in all processing stages, and then there is a validation, a final validation step of the technology in that two types of thermoelectrical prototypes will be demonstrated in relevant environments. So, what is green energy harvesting? Is the process in which energy is captured from a system environment and converted into usable electrical power. This energy can be, for example, thermal energy, and then we are speaking about thermoelectricity. So, and waste heat, as we can see here on these figures on the left and on the right, we can see that around two-thirds of the primary energy produced worldwide is lost into the environment as waste heat. You can see here in this study was published in 2016. And the most significant amount of waste heat, which is the unavoidable thermal energy, are generated in industrial and energy generation process. So if we have the capability of recovering a fraction of this waste heat, and that can be done by using thermoelectrical devices that converts that waste heat into electrical energy. That electrical energy can then be put again in the energy system to be used. So if you look now here to these figures on the left, where we can see the theoretical and realistic waste heat recovery potential in the European Union industry, we can see by temperature levels. We can see here that the waste heat can be divided depending on the temperature of that waste heat. We have low temperature waste heat, we have medium temperature waste heat, and high temperature waste heat. We can see here that the final energy consumption in the European Union, around 26% corresponds to the industry. From this fraction, we can see that almost half of that energy is lost. Some of that loose energy is lost as waste heat through exhaust or effluents. And we can see now through to the different levels of temperature levels of waste heat that the theoretical waste heat recovery potential it's higher for the low temperature waste heat, followed by the high temperature waste heat. However, the realistic waste heat recovery potential it's higher for the high temperature waste heat when compared to the other types of waste heat. So it was seen that the waste heat recovery potential in the European Union was estimated to be in the scale in the range between 300 and 350 terawatts per year. And this amount of recoverable heat has the potential to avoid tens of millions of tons of CO2 emissions. So the possibility of using a thermoelectrical device to capture and to directly convert waste heat into electrical power is a very attractive and valuable approach to improve the overall efficiency. So, in fact, the thermoelectrical energy harvesting, by turning the waste heat energy released to the environment in emissions-free electricity, it has become and it is becoming an increasingly important contributor to the progress of sustainable renewable energy ecosystems. So, and what is a thermoelectrical device? First of all, it is a solid state energy converter. robust and reliable equipment. That has unique characteristics like no moving parts, no maintenance, quiet operation, and absence of production of environmental harmful waste. And what is the design of that type of device? So it is made of several, you can see here to this schematic illustration of the thermoelectrical device. It consists of several thermoelectrical junctions, electrically connected in series, that consists of P-type and N-type thermoelectric materials, or also known as thermoelements. And when it is subjected to the heat flow will create an electric current. So here below we can see two thermoelectrical prototypes devices that were produced by two of the start partners, RGS Development from Netherlands and Technology from Denmark. So how is the thermoelectrical materials performance evaluated? It is through this what is called the figure of merit, ZT, which is a dimensionless figure of merit. And we can see here that the ZT depends on the Seebeck coefficient, the electrical conductivity, thermal conductivity, and absolute temperature. And the goal here is to maximize ZT. So a good thermoelectrical device material should have high electrical conductivity, low thermal conductivity, and large Seebeck coefficient. However, it is difficult to compromise this altogether, and we can see here on this blue curve that the maximum ZT is achieved when the square of the product of the square of the Seebeck with the electrical conductivity reach its maximum. This product is also known as power factor. We can see here some examples of state-of-the-art thermoelectric materials. The ZT of those materials is as a function of the temperature. As I mentioned before, we can see here that they consist mostly of tellurite-based compounds, bismuth tellurite-based compounds for low temperature applications. For medium temperature applications, we have lead tellurite-based compounds. And for higher temperature applications, where we have a different type of compound, the silicon germanium compounds. We can see here that the values range between 1 and almost 2. So regarding the tetrahedrite-based materials, they have excellent properties for thermoelectrical applications. Specifically, they are a p-type semiconductor. They show a p-type semiconductor material behavior. They have high Seebeck coefficient and extremely low thermal conductivity. We have here already there is available in the literature the performance of thermoelectrical tetrahedrite-based materials. We can see here that depending on the composition and on the processing conditions, ZT higher than one were already reported, have been reported. And if we compare the tetrahedrite-based materials with the current commercial thermoelectric materials, we can see that the main problems that the state-of-the-art thermoelectric materials presently show, the tetrahedrite-based materials don't have those problems. Specifically, they don't. The tetrahedrite-based materials don't show problems regarding toxicity, regarding environmental aspects, regarding its availability, and also the tetrahedrite-based materials allow the large-scale manufacture. So, however, currently we don't find any useful application for this type of materials, for the tetrahedrite-based materials. But we know that the tetrahedrite, as almost all of you know, it's a covalent ammonium sulfosalt that forms a complete solid solution with tennantite. and it is relatively abundant in some copper mine tailings. However, up to now, as I said before, it doesn't have any useful application. So it has another advantage, as I spoke and you saw on the previous table, that is regarding its geographic concentration. So it doesn't show any issue regarding geographic concentration. So we can see here on the right of on this global map that the tetrarite is very abundant and can be found all around the world. This is shown by this colored cycles here corresponding to the localities that the tetrarite mineral soils can be found. However, when we compare to the tellurite-based technology, we see that they show a problem regarding abundance and geographic concentration because China accounts for more than 60% of its production. So, what is the main relevance of the START project? So, we we are promoting a reduction in the dependence on important critical raw materials. Uh, we are promoting a sustainable use of mine tailings by converting discarded waste secondary sulfides into useful valuable products for the production of tellurite of toluene-free thermoelectrical devices that will be used to recover heat losses from industrial processes and converted them into electrical power. This will promote secure, clean, and affordable energy to fight energy poverty and encourage energy citizenship. And also, we will promote by this in this way the diversification of the sources of renewable energy production system, the green energy harvesting through thermoelectrics. What are then we are then proposing a unique technological solution that is based on the conversion of mining waste into materials for waste heat recovery, thus contributing to an efficient use of resources while promoting the use of green energy harvesting through thermoelectrics, which is in line with the European Green Deal, the EU Action Plan on Critical Raw Materials, and the EU Action Plan on Circular Economy. Here are the main impacts: reduction in EU dependence on primary critical raw materials, promotion of circular economy processes, and the production of thermoelectrical energy harvesting system to reduce fossil fuels consumption, increase the overall efficiency of energy production and consumption system, and to reduce greenhouse gas emissions. So, what are the expected main outcomes? So, START project proposes an innovative value chain that proposes disruptive technologies for the direct use of minerals in thermoelectrical renewable energy ecosystem based on a waste material waste heat to power methodology. With that, by converting discarded waste secondary sulfide materials available in Europe into useful and valuable mineral resources, we are promoting a new market opportunity. We are creating a new market opportunity for European mineral resources. With that, we expect to boost EU competitiveness on raw materials. In fact, recycling will contribute to security of supply of raw materials and will help to improve the sustainability of materials in the EU economy. START will enable the transition to a greener society and economy through economic innovation, more sustainable economic models, and by promoting energy security. And finally, START will create a new rapid growth commercial ecosystem that will attract new stakeholders exploiting market opportunities for replication and market development. So, how, how can you follow us? So, we have a web page that can be accessed through this link. There you have all the information that is available regarding the project, the consortium, the objectives, the main impacts of the project organization, some documents that will be available during the implementation of the project, the news regarding the different activities, multimedia contents like video contents, the consortium, and also there is information on how you can contact us. Of course, Start is also present in social media platforms like LinkedIn and Twitter. Um, that I advise you to follow to be updated with the most new activities of the and news regarding the project, the results and the activities. So here are the links for the LinkedIn and for the Twitter. We also have an account on SlideShare where there you can download the most important presentations and other type of documentation. And also, this is not a social media account, it is a data repository, Zenodo, that will be used as the main data repository of the open start data in order to fill the fair data principles, where there you also find all the information regarding all the information that will be published during the start project. And of course, we have a newsletter that is published every 6 months. The first issue was published last November, and there you can find very interesting information regarding the news and the project activities. We also have short technical documents from different topics that will be covered by the project activity that is covered, included in the project activities. And also you have the opportunity to meet the start partners. Uh, uh, every issue will present one or two of the partners of the start partners, and of course, as you had the opportunity to see the introductory video, we have also Starty with a comic character. So we have a comic story where Starty explains Start, the implementation, and also all the aspects, all the most important aspects regarding the activities of the start project will be here explained in a more easy way that will be understandable not by all the people, by not the technicians, not necessarily by the technicians, but by the all the people will understand here the what we try to implement on the start project. And soon, very soon, it will be available. The start comics will be available on the different language um, that are that are that are here involved in the project from each organization of the different countries. So, in order to subscribe the newsletter, you need to go to the Start web page, click on the link that says contact, and then subscribe. And then you can give your details to receive the newsletter through email. So, and that concludes my presentation. I want to acknowledge the European Union for co-founding the project, and I also to acknowledge all the different colleagues from the different from the different start partners that are involved in the activities of the start project. And also thank you for your attending here to this first webinar session. Now, if you have any question, leave it to the end of the presentation. I will now move to give the floor to Daniel Oliveira. I think, let me see. Yes, You can now share the screen, Daniel.
Okay, am I on?
Yes.
Okay, well, thank you very much, Philippe. Good afternoon, everybody, or good morning, depending on what part of the world you're in. Before I start my presentation, I have to acknowledge the people that are up on the screen as well, plus a few others that are not, but who have contributed to this specific work package, which is WP2. And that means all the partners that have identified areas in their respective countries where the possible sampling can take place. So before I say anything else, I'd like to just highlight a few words that Philippe has mentioned in his presentation, or phrases, and if you will, and if you like, you could maybe call them keywords. But a few things stick to mind, which is material intensive, it's valuable secondary raw materials, the import dependence from external European sources, and obviously the tetrahedrite tennantite series. As you will see from the presentation that follows, all these aspects are extremely important, and so let's move on. So as you can see from Philippe's presentation, Project Start has very special raw materials requirements. He's explained to you exactly why the tetrahedrite tennantite series is so important, because of its chemical characteristics. And so there's no point us trying to find a substitute for these materials when these are the materials that have shown the most promising results in experiments and research that has already been carried out. Okay, so I apologize that the changing of the slides is taking a little bit longer, so there's a little bit of a lag. But just to tell you exactly what needed to be done first is the evaluation of the site mineralogy and the suitability, obviously, of the materials that are available in these mine waste dumps for use in the thermoelectric devices. And so if you have a tetrahedrite tennantite series, and obviously we are rather focusing on the tetrahedrite, which is the antimony end member of the series, rather than the tennantite, which is the arsenic end member of the series. If these materials are available in the specific mine site, then they are suitable materials. If they are not, they are completely unsuitable. And so there's no point going to sites where you do not see these specific mineralogies appearing. So in the course of the project, we have identified already 6 countries that have potential for supplying the critical raw materials that we need for this specific project. And obviously these are shown very schematically in this map here, which is Austria, Portugal, Spain, Germany, Slovakia, and Colombia. And just to show you that these things do exist, so to speak, here are some pictures of some of the mines that were selected as possible sources of raw materials. I would, however, like to also stress that the message that is in the box on the top left-hand side of the screen is extremely important. Obtaining raw materials means mining and quarrying. They do not appear on your tables or on your kitchen or in your office or anything else by Bluetooth technologies or anything else. They need to be physically taken out of the ground. And so the people who are anti-mining and find excuses for making protests for everything related to mining, please bear this in mind. You need to dig them out the ground. How you dig them out the ground is another story, but you need to dig them out the ground. So how can we make sure that we have a suitable site for supplying these raw materials for the START project? Well, first of all, it all depends on the local knowledge of the geologists involved or the geological survey organizations. Each geological survey organization has an extremely well-founded view and evidences from their field work that shows, and they know exactly where the suitable sites might be. Obviously, you might find problems like access to areas where areas are now private, but in most cases, this is not the case. And how do you do this? By knowing exactly what the substrate is that you are walking on. And I'll just show you an example here from the São Domingos mine in South Portugal, where we have, for example, a very detailed mapping of the waste materials that are on surface, as well as the outcrops. And through various field campaigns and sampling and testing and studies, we know exactly in which area of these colored polygons we may be able to go and fetch the specific raw materials that we are searching for. When I give this example of southern Portugal, obviously the same situation exists in the other donor countries. So Austria, Slovakia, Spain, Germany, and Colombia know exactly as well where these sites are, what they might contain, and obviously the knowledge of the geological survey organizations is extremely important, because we would not want to sort of start eliminating sites. We know already that for a site to have tetrahedrites, it has to have a specific type of deposit. So you would not go and look for tetrahedrite tennantites, say in a gold mine, and it's mining waste. You need to go and look for volcanic type deposits. And obviously, once this is known, this eliminates right from the start a series of areas where this might happen or might not happen. So this is extremely important, this local knowledge of where to get. Now, however, nature is not so kind to us in every single case. Now, on the left-hand side of this images, you have what we would call pure tennantites or pure tetrahedrites. So these are homogeneous masses, monomineralic, and unfortunately, in nature, it is extremely rare that we find these monomineralic masses. And so what we do find are these complex ores where you have an intergrowth of several different minerals. And this is something that occurs over and over and over. And so the pictures on the right-hand side of the screen show you a typical type of tetrahedrite tennantite bearing deposit, with the yellow that you recognize immediately as being chalcopyrite. It also has other minerals intergrown in there. And on the extreme right-hand side, you see a microphotograph of what this ore actually looks like under the microscope. So as you can see, several different colors, a majority of say on the right-hand side of also pyrite, but you have the chalcopyrite, you have all the other, the gray minerals, which are the tetrahedrite tennantite series. So nature has a way of complicating things. This is important because in the next few slides, and here's another example of the types of ores that you can find in nature, and you can see that this is really monomineralic. It is multimineralic, and this is something that makes things slightly harder for supplying the raw materials that we need for this specific project or any other project that needs raw materials. Obviously, once you have the thin sections, your next task is to put it under the electron microprobe, and you can see once again that as you zoom into the different minerals, the complexity increases in these multimineralic ore deposits. And so you can see, for example, that you have vanadium together with the antimony, you have germanium, you have tin. And obviously, this is something that we have to be aware of once we have collected the samples and we want to supply them to the value chain that follows the primary phase. And so now you may ask, now what? Okay, so it's complex. We know where the minerals are. We know which minerals we want, and we know that they're complex. So after collecting the samples, which everyone has done so far, you have basically an image or images that look like this. You have several bags with several rocks and several pieces of the ore material within these plastic bags. And so what do you do with it next? Well, first of all, you need to separate the different minerals so that you can end up with a more or less more homogeneous sample of tetrahedrite, tennantite minerals. In this case here, I'll show you the extreme situation where the mineral, the deposit is so complex, the minerals are so small that these have to be handpicked with a set of tweezers. So in deposits where the material is slightly coarser, then obviously it makes it much easier to remove and to concentrate these samples. So you've concentrated the samples, and now how do you know for sure that you do have a tetrahedrite, tennantite samples that are suitable for the project? Obviously, the next phase is to obviously stick it under the X-ray diffraction machine or study it, and to make sure that the peaks that you obtain, and please do not look at these peaks because this is not a tetrahedrite tennantite sample that is being shown here. This is just for pictorial purposes. So you need to make sure that the peaks that you are obtaining are in fact for the antimony, the arsenic, etc., etc., etc. And obviously the sulfur will come through as well. So in terms of making this a complete story, now we have samples that are mostly monomineralic and they are suitable for the project. However, before all that, a set of steps had to be devised to make sure that the sampling protocol that is being developed is adhered to. And this consists of these three steps that you see on the slide. And so by the things that I've said so far, you can see that, for example, step one was the evaluation of the potential sites. That led then to a sampling plan. The sampling plan is obviously step two, where we check everything and we then end up sampling, and then obviously all this gets fed into step three, which is the confirmation in laboratory and the characterization of the minerals to make sure that we have the suitable raw materials for all that. And obviously all these will then feed into a step four, which is obviously the data interpretation. And then this data interpretation is really the final material that can then be handed over to the partners that are actually going to develop the thermoelectric devices. For this to happen in a consistent way, we also devised a a set of parameters that would be noted by all the different partners, and to make sure that the samples, once they are fed into the manufacturing process, so to speak, would adhere to some sort of homogeneous type of sampling. And so you can see the usual things with the deposit type, etc., etc. But then we also want to know if the sample was obviously a simple sample or a composite sample, and how many number of subsamples. And the reason the number of subsamples is here is because, well, what some partners have done is they've actually decomposed the sample into the different grain sizes through a series of sieving. And so you have samples that can be, say, greater than 3 millimeters or greater than 2 millimeters, 1 millimeter, and then you start going into the micrometer scale, and then you end up obviously with a very fine powder. So this is important. And obviously the type of mine waste, if it's waste rock, the tailings, waste rock dump, or stockpiles. And also obviously a note on the mineralogy, and obviously the photos that support all your findings up to there, and obviously a field for additional comments on the sampling sheet, should there be the need to add these in time. So once the field sample is coming to the laboratory, like I said, and this is just to explain to you the size of the size, the type of subsamples that we may be dealing with. Obviously, we can separate the samples into several fractions, size fractions. Obviously, this needs to be weight split, and then it goes for XRF, XRD, and so on and so on. And obviously, then this goes into, once everything is okay, it gets fed into WP3. So this is my final slide, and I'd just like to finish by saying that this is a slide that I used for a presentation in Chile in November last year. And what I'd like to focus on here are the final words that says from waste to high tech. And as Philippe has mentioned as well, the idea would be to eradicate the legacy of the mining footprints of the old abandoned mines that contain these materials by converting waste into high-tech devices. And with that, I thank you very much for your attention, and open for questions, of course.
Thank you, Daniel. Thank you, Philippe. Before, of course, I think we can come back to this way of seeing us, because we can go to the discussion now, and I hope there are some questions coming from the audience. I'm switching to a discussion mode. So now everyone should be able to speak if they want, just by activating their microphone and camera in case. I don't know if there are any questions. Yes, there is a question already written, but maybe Antje could give the question directly. And then I see other people coming up on the screen.
Yeah, I'm so glad that Antje's question is directed at Philippe.
I don't see Antje coming on, so I will just read the question quickly. So, okay, thank you for the comprehensive overview. The aim is to use tetrahedral rice directly, but isn't the capacity related to the individual occupation of each lattice position? Wouldn't the efficiency depend on the crystallography? Danielle has already pointed out the complexity in the natural samples. In other words, is synthesis envisaged?
Yes, of course. The efficiency of this type of materials will depend on the composition and of the uh, substitutional elements that will be present. For example, the presence of iron, zinc, and other type of elements will influence, as well as the processing conditions and processing technology that we'll use. That all will influence the final efficiency of the material and of the device, of course.
Yeah. Okay, maybe we can start with the people on the screen. I see Piotr, for instance. If you want to open your microphone as well and pose the question.
Yeah, Bruno,
Yes.
before we go there, I see there's a question in the chat by Giovanni
Also,
that
yes.
says, yes, please indicate how many samples to take. I think the answer to this question all depends on what the partners in WP3 are going to need. So if they need, let's say, 50 grams of sample, then we will give them 50 grams. If they need 1 kilo, then we will need 1 kilo. Now, depending on the type of sample, or where we source it from, obviously there are deposits that might have uh, more tetrahedrite and others that might have less tetrahedrite. So that is why it's important, and it's a challenge, to make sure that the samples, once they are collected and they are sent to WP3, or as homogeneous as possible. So different samples from different areas can be used together.
Okay.
Hello,
Yes, please, Rafael. Yes.
I'm from Brazil. I'm the representative of
Welcome.
the Geological Survey of Brazil, and I want to point out some facts that here in Brazil, looking at our database, we have only three reports of tetrahedrite in uh, in I mean in old mines, something like that. We don't have. Uh, Let me see. We have an evaluation of the products in our tailing dams, in our mine waste. We don't have a specific project for that. So we have three sites that reported tetrahedrite from academic works, uh, and I happen to know all the three sites, which are all abandoned mining, from three different states in Brazil. And I think that we have a lack of information about our mine wastes at first, because looking at these three sites that we have the tetrahedrite reported, they are they'll be they were like characterized as wastes of the ore, as ganga of the ore. So I think that in case of Brazil, we might have a huge potential from tetrahedrite that hasn't been explored, hasn't been known, you know. So I for me, my main issues are that we can have samples from these three sites. We can have, if we have a specific program to do that, but we also need to improve the characterization of our mine waste to to open up this window of occurrences. The tetrahedrite in Brazil, until now, it's also almost like curiosity. So we don't have a specific works in that subject, and I'm trying to figure out what type of of actions we can take to contribute to the project, you know? And that's it, you know. I know it's a first meeting, and you mentioned that 1st of June, 26th of April, we'll have the South America presentation. I think it's Colombia. It will be the most, I mean, most advanced one. But I think we can further improve, you know, this type of knowledge, and we are open to contribute, you know.
Thank
Yeah,
you.
Rafael, if I can just have just a few minutes to reply to you. Yeah, I understand your problem, and obviously that problem is universal. A lot of people have mining waste, and they don't have it characterized.
Yeah.
Now, the problem with the European mines up to say a decade ago was exactly that. We knew we had waste. We had not characterized it sufficiently to be able to say, okay, look, we have in this waste pile, we have so many ppms of germanium, and obviously we have a volume, and we can convert that to a grade. And this is something that needs to be done on a more systematic basis. And I understand that obviously all of this takes manpower and it takes money. And most of all, it takes time. So what the only thing you can do is you start small and build up your database. That's the only thing I can say.
Okay. Yeah, I think that's the way, you know, to begin where we know that there is, because these environments where these reports are, they have several other abandoned mine sites which hasn't been studied. So it open up the whole environment, the whole geological environment for this type of
Yeah.
occurrence. Okay, thank you, Daniel.
Thank you.
No, thank you, Rafael.
I think there are many people on the screen. So is there anyone who wants to make a question? Because I cannot understand it from here. If you can open your microphone and ask a question. Is there anyone? Yes, maybe. Antje?
If I
Yes.
may, so following also Raphael's comments, it is, in my view, something where we probably need to broaden up our, let's say, view. So because tetrahydrite has very barely been analyzed in the past, so even so it might be there. But even if it's there, it's not there in huge masses. And that is one of the reasons why I'm asking if we would go also for or considering to synthesize the material from different starting materials, including their, let's say, the sulfur series. So that would even widen the possibilities we do have. And we would have even a better control on the system and the capacity of the material.
Yeah, I agree with you, Antje. I don't know anything about this cooking of tetrahedrites, but Philippe is an expert. And I know that he can make tetrahedrites out of anything, really.
Not exactly. No, but for example, it is allowed the presence of other sulfite phases. In principle, that it's not an issue. Okay, we don't need a very pure tetrahydrite. Okay, it can accommodate other types of sulfite materials. Because the processing that we are using, which is mechanical activation, it's a high energetic processing technology, and that decomposes those phases into tetrarhodite. Of course, we cannot use the mineral as it is. We need to mix it with elements or with other synthetic materials. Okay, so we can always adjust the composition that we intend to have at the end.
Yeah, that's what I thought. So that was
Okay.
also the reason why I think it's quite, let's say, clever to look into the possibilities in the sites where you might have tetrahydrate in order to widen the applicability of the site for our purpose.
Mm-hmm.
Okay. Any more questions or comments from the others? Their attendants? No? Well, if it's actually 2 minutes after the end that we have decided for this webinar, so maybe I think we can thank the speakers and thank especially the attendants for being here for this hour. I hope you will be able to join also for the next webinars in the series. I remember you the dates, 26th of April, 1st of June. And yes, follow our website and our social media to find the news about what we are doing. We will continue in this series about the geological side of the project, and then over the years we'll move also to the other parts of the project for sure. Thank you very much.
Okay.
You want to
Thank-
close, Philippe?
No, I want to acknowledge everyone that attended to the webinar, and also to Daniel and to you, Bruno. Thank you.
Thank you very much.
Thank you.
As I mentioned in the chat, the video will be available later on the website and on the social media, so you will find it if you want to rewatch. Thanks a lot. Have a nice day.
Bye.
Have a nice day.
Bye.
Thanks,
Bye-bye.
Thank you.
everybody. Bye-bye. Keep well.